Hey guys, so chocolate ice cream. Sorry, sending my son to get me some ice cream. Anyways, you know that time when you could just use some chocolate, it makes you happy. I like chocolate. Actually, I more than like chocolate. I love chocolate. All right, so today we are on adding polynomials. So we are moving on from the radicals. Radicals and exponents were part of this unit, and they're important because they help us understand the components of polynomials, which is the next part of this unit. And we're going to use algebra tiles to add polynomials. And when we use algebra tiles, we're going to use them hypothetically, like we're going to imagine using them. We're not going to actually touch and hold them and stuff. And we're going to add polynomials algebraically as well. This is where we're going to end up landing, and this is the point where we're supposed to get to. Okay, so notice that in the solar panels at the right there are 4 squared or 16 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, each column has 4 cells. So a column is vertical, straight up and down. So each column has 4 cells. 1, 2, 3, 4, 1, 2, 3, 4, all the way. And each row has 4 cells. Okay. If a square solar panel with an unknown number of cells along the edge can be represented by x squared, how many cells would be in one column of the panel? So it's saying if an unknown number of cells along the edge can be represented by x squared, how many would be along the panel? Well, if this is x squared, they're trying to figure out, well, how many would be along a column? Okay. Well, if it's a square solar panel, we know that a square has all 4 sides that are congruent. So whatever side one of them is, they all are that same length, okay? So if this were a square, let's actually put the x squared in here because this is a rectangle, although it is actually a square because it's 4 by 4. To get an x squared as basically our area, that means we had to have an x times an x. So how many cells would be in one column of the panel? X number of cells. Okay. All right, so a square solar panel with x rows and x columns can be represented by the algebra tile x squared. There's actually an x squared algebra tile. Okay. A column of x cells can be represented by using the column tile. They label it x. So the big square tile is an x by x, so it's x squared. And then a single rectangular tile is the x tile. And a single solar cell can be represented by a +1, a +1. Okay. So it says, suppose that there were 3 square solar panels that each had x columns and x rows, 2 columns with x cells, and 3 single solar cells. You can represent 3x squared plus 2x plus 3 using algebra tiles. So if I have 3x squareds, notice how in my picture there are 3 of the x squared tiles. And then to represent the 2x, there are 2 of the x tiles. And then to represent the 3, there are 3 of the +1 tiles. Number 2 says represent 2x squared minus 3x plus 2 using algebra tiles. Draw a picture of the representation below. So I need 2x squareds. So I'm going to need, okay, go with Daddy. So I'm going to need 2 of these. Now I need to represent a negative 3x. So I am going to be using the blue ones that I traced there, the x tiles, but in person, if you were to play with these tiles, I don't know if any of you have played with these before, when you flip them over, one side is positive and one side is negative. And usually the negative side is red, but I'm just going to keep the same color, and instead of just writing an x, I'm going to put a negative x inside of it. And I need 3 of those. And then plus 2, so I need 2 of the +1 cells. And this represents 2x squared minus 3x plus 2. Okay, notice that these obviously are different from the negative x's, which are different from the plus 1's. Turn it over. Okay, so now it says adding polynomials using algebra tiles can be done by modeling each polynomial, identifying and removing zero pairs, and writing the new polynomial. So example A goes through all that using algebra tiles, but really all they're doing is grouping like terms. That's what the algebra tiles are for. That's what they're meant for you to see. They're meant for you to see visually that a 3x squared is different from a 3x, which is different from a 5. They're completely different terms. So the x squareds are all like terms because they're all the same size square. The negative x's are like terms because they're all the same size rectangle. And then the plus 1's are like terms because they're all the same size solar cell tile. Okay, so that just means that they're like terms. I can add up the blue ones because they're all the same type of term. I can add up the green ones because they're all the same type of term. I can add up the purple ones because they're all the same type of term. That's basically what you're supposed to get from the algebra tiles. So let's go ahead and take a look at the Try These A, and let's try it. It says to add using algebra tiles, but we're going to add without using algebra tiles. We are going to combine like terms. Okay, so we're going to start by grouping. We're going to look for the like terms. So x minus 2 plus 2x plus 5. Well, x's are like terms because they both have an x. Okay, when there's no number in front of a letter, we assume it to be a 1. So 1x plus 2x equals 3x. Okay, and then we have these numbers, a -2 and a +5. Numbers are called constants, and they're called a constant because this is constantly a -2. This is constantly a +5. So we know exactly what it is. It's constant. A constant doesn't change until you add or multiply something to it. But yeah, so -2 plus 5, if we add them together, is a +3. So that adds up to 3x plus 3. Okay, this one goes up a degree. So we have 2y squared. That's a like term with the 3y squared. So I'm looking for all the ones that have the same degree pretty much. The degree means the power on the exponent, which you guys know. We did exponents not that long ago. That was the beginning of this unit. So 2y squared plus 3y squared is 5y squared. Notice how the only thing that changed was the number in front of the letter. The exponent stays the same because we're not multiplying, we are just adding. So we're just adding like terms. We're adding up how many y squareds there are, pretty much. All right, 3y, this is the only y term in there. So we're just going to write it down. We never disappear things for nothing. So don't make something disappear for no reason, okay? Okay. All right, so we have a +6 constant and a -4 constant. If we add those together, 6 minus 4 is a +2. These are easy, right, guys? So easy. If this is not easy to you, you need to come to tutoring. You need to come see me so I can make it easy for you guys. All right, this one, let's see. Let's look at all the x squareds. I've got a 2x squared and a -x squared. So because there's no number, but there's a negative sign, that just means that this is a -1x squared. So 2x squared plus a -1x squared is just a 1x squared. Now you can write the 1 in front It's not going to hurt anything, but you're not going to see me do that a whole lot. Anytime you see a letter with no number in front, you always need to assume that it's a 1. Always, always. All right, and then we have a 3x and a negative 4x. So 3x plus negative 4x is a negative 1x. Again, you don't need to put the 1. I'm only doing it for right now, but pretty soon you won't see me do that anymore. And then 9 constant plus a negative 6 constant is a positive 3. So the answer would be x squared minus x plus 3. Okay, when there's a 1 in front of the x, I'm not going to write it from here on out. Okay? All right, so now I always start with the highest exponent, the highest degree. And the highest degree I see are these x squareds. So this one doesn't have a number in front, so that means it's a 1x squared. 1x squared minus 3x squared is negative 2x squared. Okay. The next term I see that goes down, the next degree higher is the x, all the x terms. Negative 3x plus 2x is a negative 1x. And then I have my constants. I have a positive 5 and a positive 4. 5 plus 4 is a positive 9. So the answer is negative 2x squared minus x plus 9. So what I did here, when I was combining like terms, you know how I started with the term that had the highest degree, and then I would write that? Well, whenever you go from highest degree down to lowest degree, that's called standard form. And you are always supposed to write your answers in standard form. Make sure it's proper. When you have more than one letter, like none of these we have more than one letter. These were all the same letter, either X's or just Y's in each line. But whenever you have more than one letter, you always go alphabetical order. Students always ask me that. Well, what do you do if you have an X and a Y? Whatever goes first in the alphabet is what you write first, pretty much, if that happens. Okay, turn the page. Number 3. Can you use algebra tiles to add 4x to the 4th plus 3x squared plus 15 plus x to the 4th plus 10x cubed minus 4x squared plus 22x minus 23? If so, model the polynomials and add. If not, explain why. So the point of this question is to show that algebra tiles only go up as high as an x squared. So the algebra tiles are a way to get you used to the idea of combining like terms. But it's only to get you started. It's not to help you do these. It is to help you do these problems too, but once they get to a higher degree, you're expected to know, oh, I'm looking for those like terms now, the higher ones, and that you're just making that connection. So no, we can't use algebra tiles to solve this, but we can combine like terms like we've been doing in the last examples. So I'm going to start with the highest degree is an x to the 4th, and there's a x to the 4th here too. There's no number in front of that, so it's a 1x to the 4th. 4x to the 4th plus 1x to the 4th is 5x to the 4th. Okay. The next degree down, I see an x squared, but I thought I saw, yep, an x cubed. This one's the only x cubed term, so you just bring it down, plus 10x cubed. And now we can do the x squareds. We have a 3x squared and a negative 4x squared. Positive 3x squared plus a negative 4x squared is a negative 1x squared. And then do I have an x term? That's a constant. There's an x term, the 22x. So I'm just going to bring it down, plus 22x. Oops, why aren't you focusing? There you go. And then my constants, I have a 15 and a negative 23. Oops, I put 4 lines on that one. So positive 15 plus a negative 23 is a negative 8. And there is our polynomial. 5x to the 4th plus 10x cubed minus x squared plus 22x minus 8. All right, like terms is what we've been using. Already mentioned this vocab term often already in this lesson. It says like terms in an expression are terms that have the same variable. Same variable and same exponent for that variable. All constants are like terms. So if it's a 1,000 or if it's just a 5, they're considered like terms. We can add or subtract them. So number 4, it says state whether the terms are like or unlike terms. So let's take a look at A. 2x and 2x cubed. Are these like or unlike? Well, they both have an x, but this is an x to the first power and this one's an x to the third power. So that means that they're not like terms. These are unlike terms because they're different degrees. Different degrees. Letter B, 5 and a 5x. Well, 5 is a constant. 5x, this one has an x. The constant does not. So these are unlike terms. One is a constant. Only constants are like terms, and 5x is not a constant. Letter C, a negative 3y and a positive 3y. Well, they've got the same variable to the same degree, so these are like terms. And I'm even going to take that up a notch and be like, yep, those are like terms. I'm going to highlight them. Letter D, we have an x squared y and an xy squared. Are those like terms? Well, look at the x's. This x is an x squared. This x is just an x to the first. So automatically, these are not like terms. They don't have the same degree. Same with the y's. The first y is a y to the first, and the second y is a y squared. So those are not like terms. So unlike, that's because we have different degrees on both those x's and y's. Letter E, the number 14 and the number negative 0.6. So these are considered like terms. They're both constants. They're a number. There's no letters. They're numbers. Just because one of them is a decimal doesn't mean we can't add them. So let me highlight that one. Like. And then letter F, a 3x squared and a 4y squared. Well, the 3x squared has an x and the 4y squared has a y, so these are definitely unlike terms. They don't have the same variables. So we'll put different variables. Okay. So, using vocabulary from this activity, describe a method that could be used to add polynomials without using algebra tiles. So, the method to combine polynomials without algebra tiles is what we've been doing, and that is combining like terms. And I'm going to call this for short from here on out CLT. So it's not a BLT, even though that might sound good right now. It's CLT, combine like terms. So I'm always going to say CLT. So hopefully you watch this video and you catch on to that, because otherwise if you didn't watch this video and I say CLT, you're not going to know what I'm saying. All right, example B, it says use the properties of real numbers to add polynomials algebraically. Okay, so they do this whole arrow thing, but we already know what we're doing. We've already been doing it. We're just combining like terms. I like to underline the terms that are alike in different ways like I showed you in the previous examples. So I'm going to just continue doing that. We're just going to go straight to try these B. Notice how it says add and write your answers in standard form. Remember how I said that is highest degree down to lowest degree. Okay. All right. So letter A. It says 4x squared plus 3 plus x squared minus 3x plus 5. So I'm going to start with the highest exponent. The highest degree is that x squared. So we have a 4x squared and a 1x squared. 4x squared plus 1x squared is equal to 5x squared. Okay, so there's that first term. Next term, the next degree down would be to the first power, which is just the x. And that's the only x term in there, so we're going to bring it down, a minus 3x. And then constants. We have a 3, positive 3, and a positive 5 that we need to add together. 3 plus 5 is 8. So 5x squared minus 3x plus 8. Letter B. Okay, 10y squared plus 8y plus 6 plus the quantity 17y squared minus 11. So we have 10y squared and 17y squared. Add those up and we'll get 27y squared. And then let's see, the only y term I have is 8y. So just bring it down, plus 8y. And then the constants, I have a positive 6 and I have a negative 11. 6 plus a negative 11 is a negative 5. 6 plus negative 11 is the same thing as saying 6 minus 11. A negative sign always overpowers a plus sign. All right, next one. We have a 9x squared. Do we have any other x squareds? Yes, right here, a negative 13x squared. So 9x squared plus negative 13x squared, or 9 minus 13, is a negative 4x squared. And then I have a 15x plus a negative 11x, or 15x minus 11x, and that is a positive 4x. And then my constants, 21 and a negative 26. 21 plus negative 26, aka 21 minus 26, is negative 5. So my answer is negative 4x squared plus 4x minus 5. Okay. Are the answers to try these be polynomials? Well, the reason why they're asking that question is because of this math tip over to the left. It states that polynomials are closed under addition. A set is closed under addition if the sum of any two elements in the set is also an element of the set. So basically they're saying when you take a polynomial, pretend that's a polynomial, and you add it to a polynomial, the answer is a polynomial. Okay, so when we're adding two polynomials together, are we getting a polynomial? Yeah, as long as we have the variables with different exponents, yeah, it's a polynomial. Okay, so the answer is yes. I just justified my response out loud, so I'm not going to write it because I don't feel like it today. Explain why the sum of two polynomials will always be a polynomial. Well, we're going to explain down here anyway, so it don't matter. So basically what we're going to say is the sum of two polynomials, I'll move my hand in a second. I'm left-handed, I'm sorry. The sum of two polynomials will always result in a polynomial. You can even put that in your own words if you want. When you add two polynomials together, you get a polynomial. As simple as that. You like it when it's simple, right, guys? All right, let's turn this page if I can grab it. There it goes. All right, so we're at the end here. So your assignment is going to be on this page, and you're going to be doing numbers 8 through 18. You're going to have one more lesson this week. It'll be 4.3 as well. So good thing these are short and simple. Have a good one.